Okay, we're going to do something today which blew me away the first time that I saw it. Okay, I can't remember how old I was, but it really rocked my world, and maybe this will do the same for you. Who knows? Let's count this collection of things. I have one more in each row. So right here I have one, and then I have two, and then I have three, and then I have four. Here I have 5, 6, 7, 8, 9. Seems kind of silly, doesn't it already? 10, 11, 12, 13, 14, 15, 16, 17, and of course we could keep going. Here's the question I want to ask you. Why is it that when we count things like that, why is it that all the way up to this point do we use a different symbol? I could have actually started with no things and there would have been 0 there. I guess maybe I should have just put a little block there and there's 0 things. But anyway, so I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 different little symbols there. And then once I get to this many things, then instead of coming up with a different symbol, like I used to be able to make stars, or this, or this, or whatever else, instead of other more symbols, we start using the same symbols again. What do we say here? We have one group of 10 with none left over, one group of 10 with 1 left over, one group of 10 with 2 left over, and so on. Okay? Why do we just use 10 symbols and then start reusing them? What if we didn't? What if we only had this many symbols? I have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, what if I use only that many? Then, how would I express these numbers? Let's go ahead and do it. I would have 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, and now, what do? I say, I have one group. What did we do here? We said we had one group of 10 with none left over. Here I would say, with 8, I have one group of 8 and none left over. So this ended up saying one group of 10. Now it's going to be one group of 8 and none left over. This is one group of 8 with 1 left over. This is one group of 8 with 2 left over. One group of 8 with 3 left over. One group of 8 with 4 left over, one group of 8 with 5, one group of 8 with 6, one group of 8 with 7, and now I have 16 is what? That's 2 groups of 8, isn't it? So that's 2 groups of 8, 2 groups of 8 with 1 left over. So this would be counting if instead of having 10 things to work with, if I only have 8 things. So this is called base 10, and this is called base 8. Base 8. Okay? Let's try it with base 5 and see once what we get. Okay? So we're going to go, here's our symbols. Here's our 5 symbols. Okay? So we're going to go 1, 2, 3, 4. Now I have one group of 5 with none left over. One group of 5 with 1, one group of 5 with 2, one group of 5 with 3, one group of 5 with 4. As soon as I get to 10, that's 2 groups of 5. 2 groups of 5 with none left over. 2 groups of 5 with 1, 2 with 2, 2 with 3 left over, 2 with 4 left over. As soon as I get to 15 things, which is right here, that's going to be 3 groups of 5. So there's 3 groups of 5. 3 groups of 5 with 1 left over, 3 groups of 5 with 2 left over. Okay? So that's base 5. So here's a question I have for you. It looked like instead of base 10, we had a choice for any base for counting. Why did we choose base 10? Is there anything special about 10 that was especially nice? And the answer is no, it really isn't. The reason we did it, can you think why? Let's see. The reason is because we just happen to have 10 fingers. So you can imagine historically what happened when people were maybe counting sheep. They were off in the distance and they were keeping track of how many sheep, and they were just kind of putting up fingers. So there's, okay, I'm counting, I see this many sheep. And now that you have all your fingers up, what you might do? Maybe you put a rock in your pocket, and now you have a rock in your pocket, and now you start keeping track again on your fingers. And so by the time you're done, you're basically saying, I've got 7 rocks, which is 70, plus another 4, so I've got 74. So the fact that we have 10 fingers is what led us to using base 10. So there's nothing mathematical about it, nothing any better or worse than anything else. It just happens to be the number of fingers we had. If you ever watch The Simpsons, they have a total of 8 fingers, 4 on each hand, and so they would obviously have base 8 if they would have counted in their world. Okay? So now that we have the idea, let's see what base 3 would look like. Okay? And again, as I've asked you to do before, I would encourage you, go ahead and turn off the video and see once if you can do it on your own. If you can do these last couple on your own, it means you've really caught on to the idea. So here we go. So here's 1, 1, there's 2. Here's the number of symbols we have. Those are the only ones we have now. So by the time we get to 3, we're at one group of 3 with none left over, one group of 3 with 1 left over, one group of 3 with 2 left over. By the time we get to 6, we're at 2 groups of 3 with none left over. So there's 6. Here's 7, which is 2 groups of 3 with 1 left over. 8 is 2 groups of 3 with 2 left over. And by the time we get to 3, now what do? I can't say 3 groups of 3 because we don't have this symbol. What did we do with 10s once we got to 99? That was 9 groups of 10 with 9 left over. Then what did we do? Then we had to say 1 group of 10 squared, right? If you're in base 10 and you have the number 458, this is what? This is 4 times 10 squared, that's 400. This is 5 times 10 to the first power, and then this is just 8, or 8 times 10 to the 0 power, if you want to think of it that way. And so we'll do the same thing here. 9 is 3 squared. So 3 squared means 1 group of 3 squared with none left over. Why does it seem to keep getting more and more crowded as I go? I've got all that distance here. There's a 9 right there. Here's 10. 10 is going to be 1 group of 9, like that. 1 left over. 11. Going to look like that. 12 is 1 group of 9. 12 is 1 group of 9, and then you have a group of 3. Group of 3 is, right there is a group of 3, and then none left over. 13 is going to be a group of 9, a group of 3, plus 1 left over is 13. 14 is going to be, 1, 1, 2. So that's 9, 10, 11, 12, 13, 14. 15 is going to be what? 15 is a 9 plus 6. And 6 is 2 times 3, isn't it? So it's going to be 1 group of 9, that's right here. 2 groups of 3, that gives you the 6, with none left over. 1, 2, 1 is 16. And 1, 2, 2 is 17. Okay, there you go. Okay, so that's base 3. Okay, I'm going kind of fast. I don't have any people here to slow me down. So this is where you can just shut off the video and look at it again if you need to in order to get a little more practice. Okay, let's make this line a little straighter. There you go. Okay, now base 2. Base 2. I left that one, well, not quite for last. Those are the two symbols. So let's think about base 2 before we go too far with it. So we're only kind of have zeros and ones. Okay, this is going to be 2 to the 0 power, which is 1. This is going to be 2 to the first power, which is 2. This is going to be 2 squared. 2 squared is 4. This is going to be 2 cubed, just like if you were in base 10, this would be 5,000, which would be 5 times 10 cubed. So this is going to be 2 cubed, which is 8. This is 2 to the 4th, which is 16, and this is 2 to the 5th, which is 32. And we don't have to go beyond, I guess, yeah, there we go. We'll be good. Okay? So, let's think what we want here. So we're going to start with a 1. Then here's a 2. A 2 is 1 right there and 0 here. Then a 3 is going to be 2 plus 1 is 3. It's like that. 4, well, you have to go all the way here to 4. So here's 4 right here. Okay? 5 is going to be what? 4 plus 1? So it's going to be a 1 here, a 0, and a 1. So 5 is going to be 1, 0, 1. 6 is going to be a 4 and a 2. 7 is going to be a 4, a 2, and a 1. 8 is going to be what? 1, 0, 0, 0. Like that. Oops, I'm getting off, aren't I? Should have given myself a little more room here. Here's my 8. Here's my 9. 9 is going to be 1, 0, 0, 1. 10 is going to be 1, 0, 1, 0. There's 8 and 2 gives me 10. 11 is going to be 1 more than 10. 12 is what? A 12 is an 8 and a 4. So there's my 8. There's my 4. None left. 13 is going to be this same number, but with a 1 left. 14 is going to be this same number, but instead of a 1, I'm going to get a 2. 15 is going to be, oops, 16, look at what 16 is. 16 is 1 there, and then 4 zeros. So 16 is going to be 1, like that. And finally 17 can look like that. It's going to continue on. This one here is especially important because why? Can you think of why? You maybe know why already. It's especially important because it's the way computers count. And why don't they count in base 10? Why do they count in base 2? The reason they count in base 2 is because all a computer does is have a whole bunch of little switches which are either on or off. And so it's all built on electricity, obviously. And so you have a little switch which is either on or off. If it's on, that gives you a 1. If it's off, that gives you a 0. And since we have on and off, we can say that things are either 1 or 0. And so with that, we can count in base 2. And so everything computer is on or off like that. So there you go. So so there's one more base that I'm also going to show you, which is the base which is larger than 10 in size. So this is base 16, and so now we can go back to our 10 again. 1, 2, 3, 4, 5, 6, 7, 8. That's 8. 9. Why am I running out of room? That's really strange. There's a bunch of room over here. Here they're all pushed together and I'm going straight across. That's because there's curvature of space. There's 9. Here's 10. Here's now. What did we do here? Here we had 11, but instead of 11, we're going to give ourselves a new symbol. And here's the symbol for 11. Here's a symbol for 12. Here's a symbol for 13. Here's a symbol for 14. Let's see. Oops, I messed up. I didn't have a 10. I needed this for my 10. 10, 11, 12, 13. Sorry. I'm thinking base 10 yet. There's 10. Here's 11. Here's 12. Here's 13. Here's 14. Here's 15. And finally, when I get to 16, that's when I'll finally say one group of 16 and none left over, one group of 16 and one left over. And the reason why 16 is another kind of an important one is because since computers use base 2, 16 is 2 to the 4th power. So we often use base 16 as well, and we like to give that a name. We call that hexadecimal. Hexadecimal. I don't know why decimal shouldn't even be in there, but 6 obviously belongs there. It's 6, hex is 6, and then maybe 6 plus 10 or something like that is the word. Okay, so now that's kind of cool. And the first thing I want to mention to you is this: when we looked at prime numbers, we noted that this many things was not a prime number, but this many things is a prime number. Those are basic truths which are true no matter who is saying it, no matter what words you use, no matter what culture you are. If we were to send something out on Pioneer 10 outside of the universe and want someone else to know that we're intelligent life, well, I guess if they'd see a spaceship, they would probably assume that we must be intelligent life in order to make a spaceship. But anyway, if we wanted to start trying to communicate to them, we might begin by talking about prime numbers, because we would know that the numbers would be prime for them just as much as they are for us. Okay, it's totally an absolute true fact about existence. Okay, on the other hand, the number of things you use for counting, whether you use 10 symbols or 8 or 2 or 16, that's totally a matter of convention. Okay, it's just a matter of choice, and different cultures could choose different things. Different planets could use different things. Whatever. I'm not sure historically whether everyone used base 10 or not. But anyway, that's totally a matter of convention. There's no absolute truth to it. It's just that everyone decides to do the same thing. Just like everyone decides to ride on the right side of the road here in the United States and they drive on the left side of the road over in Britain. Okay, it's kind of their choice. So I like these two examples, prime numbers and base 10, because it gets me thinking about other things besides numbers. What about the world of ethics and morality? Okay, what things in the world of ethics and morality, what are the things that are like prime numbers, which are absolute truth? And what are the things which are just convention? As I said, the fact that we all go on the right side of the road, you get in trouble over here by not doing that, not because there's something absolutely wrong with driving on the left side, it's that we all agreed to drive on the right side, so if you do, you're going to be putting lives in danger, okay? But we could have all decided to drive on the left instead. On the other hand, so this was just our choice as a culture. On the other hand, what about murdering people? Is that just a choice we're making in our culture? And we're just choosing, yeah, let's go ahead and just say that murdering is wrong, we're going to get punished for that? Or is there something absolutely wrong about that, which would be wrong no matter what culture you're in? If you were to go meet people from another planet. It would be wrong for them to murder as well. It has nothing to do with convention or choice. It's some absolute about the world. Okay, what do you think about that? I like to ponder those things, and mathematics just gives me kind of a nice framework from which to ponder them, because as I say, base 10 is convention, prime numbers are true, absolutely true, and so how does that apply to things other than math? So anyway, I wanted to mention that. Here's another thing. How do we convert from one base to another? We'll go a little more practical now. If you wanted to, let's just use base 2 and base 10, since those are maybe two of the most important ones. Remember what base 2 is. Here's base 2. So here's 1s, 2s, 4s, 8s, and 16s. So if I have, for example, 27, how would I write that in base 2? I would take 27 and notice that I can get 1 16 out of there. So there's a 16. Once I take 27 and subtract 16, I'm left with what, 11? Yes, 11 has a group of 8 in there. So now I subtract my group of 8, I'm left with 3. So there's no groups of 4, but I do have a group of 2 and a group of 1. So there's 16 plus 8 plus 2 plus 1 gives me 27. See how that works? Let's just do one more, just for a little larger numbers. So here's 32. Let's go 2 more. Here's 64. So what if I choose, let's just take 100. Here's 100. In base 10, what would that be in base 2? Okay, let's figure out what it would be in base 2. So notice I can get a 64 out of there. So there's going to be one group of 64. I subtract 64 from here. I'm left with 36. A 36 has a group of 32 in there. So now I subtract 32 from 36 and I'm left with 4. So there's no 16s, no 8s, one group of 4, and that takes care of it. And so there's 100. See that? So there's 100. So that's how you go in that direction. Going from base 2 to base 10 is even easier, because you just have any old number you want. Let's just choose a number 0, 1, 1, 1, 0, 0, 1. What number would that be in base 2? It'd be 32 plus 16 plus 8 plus 1, which is 10, 17, carry the 1, 3, 4, 5. See that? So that would be 57 in base 10. Okay, so that's how you convert back and forth. So it's not bad. Okay, it's even easier to convert back and forth between base 2 and base 8 and base 16, because 8 is 2 to the 3rd power and 16 is 2 to the 4th power. So they were already inherent in base 2. So let's take a number in base 2. Let's take, for example, 1, 0, 1, 1, 1, 1, 0, 0, 1. Okay, take that for an example. Okay? So what is that in base 2? In base 2, what do we do? This is a 1. There's our 2s, 4s. This is 8, 16, 32, 64. That's 128 and 256. So in base 10, what would this be? It would be 256 plus 64 plus 32 plus 16 plus 8 and then plus 1. So you add all those together, you get 10, 20, 27, carry the 2, you get 11, 12, 13, 14, 15, 16, 17, carry the 1, 377. So in base 10, put a little 10 there just to indicate base 10. Like that. It's 377. Okay? Now, just to show you how you can convert this easily to base 8 and base 16, here's what you do. Since 8 is 2 cubed, right? 8 is equal to 2 cubed. All that means is you basically just take groups of 3 here. There's a group of 3. There's a group of 3. And there's a group of 3. And for each one of these, you say, if this is in base 2, what does it become in base 8? So this is just a 1, so that would be a 1 in base 8. This is a 1, 1, 1. What's 1, 1, 1 in base 2? That's equal to 7. So that's a 7 in base 8. And what is 1, 0, 1? 1, 0, 1 is a 5. So that would be a 5 in base 8. So in other words, this would be just 5, 7, 1 in base 8. Let's check it out to make sure. So this 1 means you have a 1 there. 7 means if you have something in base 8, it means 7. If you have 5, 7, 1, this means it's a 1. This is how many 8s you have, and this is how many 8 squareds. What's 8 squared? 8 squared is 64. So this is how many 8 squared you have. So you have 7 8s. 7 8s is 56. And then you have 5 times 64. What's 5? I'm running out of room here. What's 5 times 64? Is 20. Carry the 2. 340. 320. 320. So you add those together and you're going to get 7, 7, 377. See that again? So 571 in base 8 is the same as 377 in base 10. If you wanted to do it in base 16, then you just take chunks of 4. So you take this chunk, 1, 2, 3, 4, that chunk, and then 1 left over. So in base 16, what do we have here? This is 8 plus 1 is 9, so this is 9. This is 0 like this, which is 7, and that's 1. So it would be 1, 7, 9, and that's in base 16. Let's check it out. If you take 1, 7, 9, you're going to have a 9. Then you're going to have a 7 16s. How many? 16 times 7 is what? 2, carry the 4 is 112. So you're going to have a 112. And then you're going to have one group of 16 squared. 16 squared is equal to 256, I believe. Let's check it out to make sure. 16 times 16 is 6, 3, 96, 1, 6, 256. So you have one group of 256. And let's see what that adds up to. That's 11. 11 and 6 is 7. Carry the 1. 5, 6, 7. 377 in base 10 again. See that? So the point is you can just take chunks of 3 or 4 to get into your base 8 or your base 16. So that's a quick overview, and you can do more practice like this in class, but this gives you a sense of what bases are all about. By the way, here's a fun kind of problem. How high can you count on your fingers? Okay? If you just counted the simplest way, you'd count up to 10, and then you'd have to start using your toes. When I was a kid, I learned that if I wanted to count higher than 10, I did it this way. I'd count 1, 2, 3, 4, 5, and then I'd say, here's one group of 5. 6, 7, 8, 9, 10, there's a second group of 5. 11, 12, 13, 14, 15, there's a third group of 5. And then a fourth group, and then finally if I had a number like this, it would be 4 groups of 5 is 20, plus 3 is 23. So that way I can count up to larger than 10. If you count with base 2, just by having each finger be either up or down, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so this is my 1s, 2s, 4s, 8s, 16, if you use both hands, 16, 32, 64, 128, 256, 512. So this finger all by itself is a 512. By the time I have all my fingers up, it'd be 1,023. So you can count up to 1,023 by just using the fingers on your hands going up or down. So kind of cool. Okay, very good.